Hello. What you're about to watch will be the third project that I've done on the WISARD architecture. I've wanted to teach WISARD how to play noughts and crosses, or tic-tac-toe for any American watching, for some time now, and I've finally got round to doing it. It takes a bit of jiggery-pokery, but it can be done. Here's the obligatory push for the video tutorial on the WISARD architecture. You really need to watch that if you want anything you see in this project to make sense. Also, various functions and variables are used in this project that were used in the original WISARD project from 2 weeks ago. I won't be explaining those again here, so it's well worth watching the video for that project before continuing with this one. Both the links for these videos are in the comments below. Here's how to teach WISARD to play noughts and crosses. You'll recall that WISARD takes its input from a binary pattern and passes it to a series of content addressable memories, each of which produces a 1 or a 0 for the pattern presented. In principle, it should be easy. A WISARD network is given a set of discriminators for each of the 9 board positions. The addresses are set up randomly, and the memory contents for each discriminator is set to 0, as you do with WISARD. Then a human plays against WISARD, and with every move the human makes, the grid position is then passed to WISARD. The discriminators are run, and whichever grid square gives the highest score for its discriminators, that's the computer's response. Easy, eh? Well, no, obviously not. There are several problems with that glib description. Firstly, how do you represent the grid in the form of a binary pattern? You can't just have 0 for the computer's moves and 1 for the humans, or vice versa. How would you represent the blank squares? We need 3 possible values for each grid position, which means 2 binary digits. We could use a double 0 for a blank square, and a 0 followed by a 1 for the human moves, and a 1 followed by a 0 for the computer moves. Of course, this leaves a 4th possibility, a double 1, which will be wasted, since we only need 3. This means that while the game grid can be represented by 9 numbers, what WISARD sees will need 18. There might be some way of compressing that slightly, using that spare 4th combination, but let's not make things any more complicated than they have to be. Now the second problem. The discriminators start off in a completely blank state, which means that they play a lousy game of noughts and crosses. We certainly can't assume that the human opponent is prepared to throw a few games, just so that WISARD can win often enough to learn to play reasonably well. No, the human will defeat WISARD at every turn, or at least force a draw, so that WISARD will never learn any winning moves at all. That problem has a fairly easy solution too. We don't train just one WISARD network, we train 2. The first one contains the strategy for the winning moves, and on the rare occasion that the computer wins a game, that network will learn the game positions that allowed it to happen. The other network learns strategies for losing games. On the far more common occasions that the human wins, this second network will learn the board positions that made it happen. When playing any game, the computer's score for each board position will consist of the win network score for that position minus the lose network score for the same position. Then the board position with the highest score is chosen as normal. As the computer loses more and more games, it will get more and more adept at spotting which dismal board positions to avoid. If a game is drawn, then neither the win nor the lose network is updated. As always, the nitty-gritty starts with a view of the screen. The playing grid is at the top left, with buttons below it for new game and to save and load the discriminators. It's a good idea to save those discriminators often while training WISARD, as it takes an absolute age to learn to play even semi-reasonably. Below that there is a text area, which is used for saving and loading. You should be very familiar with that by now. The playing grid consists of 9 cells, 3 in each row, and rather than label them as rows and columns, as I have done before, it's easier simply to label them from 0 to 8. I've placed the HTML code for the first row of the playing grid on the screen, so that you can see how the graphics are named. Each cell is initially set to a blank square graphic, but this is changed to a blue C for the computer's move or a red H for the human's move. The graphic has an on-click property, so that the human chooses his moves by clicking on the square. This then alters the grid in memory. Test to see if the human has won, and, if not, gets the computer to respond with a move of its own. OK, on to the code. starting with the global variables, of course. Here they are. Blank, human, and computer are constants representing the different states of the playing grid, used to make the code more readable. Array GD will be the game grid itself, with 9 cells, each of which will be blank, human, or computer. However, the winning net and the losing net don't see that. They see array pattern, which holds the same thing in pure binary form, as discussed above. In this graphic, GD will be what the user sees on the left, and pattern what the program gets on the right. Take a look at array stored position. This will hold the state of array pattern after the human has made each of his moves and before the computer has had a chance to respond. This is needed so that after the game, win or lose, the appropriate wizard net can be trained. Of course, we will also need to know what move the computer responded with, so that either WinNet can learn that that was a good response, or LoseNet can learn that it was a bad response. These responses take the form of the grid position that the computer chose, and are stored in array stored response. The variable numStored tells the program how many stored values there are. As such, it points to the first empty slot in both stored position and stored response. This is because the array elements are numbered from 0. So if numStored is 0, it means that there are no stored game positions, and yet numStored will point to the first element in the array. There are 18 sets of discriminators in the program altogether, 9 for WinNet, representing the different board positions, and 9 for LoseNet. Although each set of discriminators only gives a score for one board position, that score must be calculated based on the entire board layout. So the set must have a total of 18 inputs, spread over all the discriminators within that set. I have made the arbitrary decision to give each set 6 discriminators, each of which has 3 inputs, as 6 times 3 gives a required 18. The first things to do are to run functions newGame and initialize discriminators. newGame simply clears the game grid on the screen and the arrays GD and pattern. It also sets numStored to 0, thereby resetting those two lists as well. You might have noticed a global variable called winner a couple of screens ago, giving the identity of the winner, and that's not reset here. It doesn't have to be, as that variable is set or reset as needed in function checkWinner. More on that later. The variable winner just has to be global, so that it can be referred to here, there, and everywhere. One thing function newGame doesn't do is fiddle with any of the discriminators. This is so that we can have one new game after another, while the discriminators gradually adapt to play better. The discriminators are set up by function initializeDiscriminators. In fact, this function is rather short, as it gets function setUpDiscrims to do the donkey work. setUpDiscrims creates a set of discriminators for one board position for either the winning wizard or the losing one. InitializeDiscriminators goes through all 9 board positions and calls setUpDiscrims for each position, once for the winning net and once for the losing net. Here's function setUpDiscrims. The first thing it does is to arrange the numbers 0 to 17 in a random order in array nums. I won't go over how function randomList works, as it's already been explained to death in the previous 2 projects. Suffice it to say that you can read through the values in nums in order to get the numbers 0 to 17 in a random order. A loop goes through each of the 6 discriminators for that particular board position. It sets the 3 inputs for each discriminator to random positions across the array pattern, placing them into an array imp for that discriminator, and blanks the contents of the memory for that particular discriminator, the memory being stored in array values inside the discriminator. And all this is done in a temporary variable called temp. The last thing that happens is that temp is reassigned to the actual discriminator that was passed as the parameter. So, the game board is blank and on the screen, and the discriminators have all been set up with input addresses assigned. Let play begin. A message has already been displayed at the end of the function newGame, telling the human player to make the first move by clicking somewhere on the grid. When that happens, the function choose is called, with the parameter being the grid position where the human clicked. First, the computer tests to make sure that the player has clicked on a blank square. I wouldn't put it past that sneaky human to click on a space already occupied. Assuming that he has, several things happen. The appropriate cell in array GD is set to human, and the corresponding graphic changed on the screen. The two cells in array pattern are changed to 0 followed by 1 to indicate that the human claimed that square. Or rather, only the second one is changed to 1, as the first cell already contains 0. The array was wiped clean in function newGame, remember? Then the board is checked to see if the human has won using function checkWinner. Of course, if this is the first move, that won't be the case, and the global variable winner will be given the value 0 to indicate that nobody has won. However, function choose is used on subsequent human moves, one of which could be the coup de grace that wins the game. Assuming there's still everything to play for, the program stores the state of array pattern and then starts to formulate its response. This gives a sizable number of functions to explain. I'll start with function checkWinner. It's as good a place as any. The single parameter is the side that the function is supposed to be checking for, either human or computer. There's no point in checking to see if the computer has won directly after the human has played his move, or vice versa. The code looks very complicated, but it actually consists of a series of statements that test sequences of 3 board positions to see if they all contain the parameter value. It can be compressed a little by spotting patterns. For instance, checking cells 0, 1 and 2, then cells 3, 4 and 5, then cells 6, 7 and 8 can be done by the same lines of code with a slight tweak. Similarly, checking down the columns. There are only 2 diagonals to check, however, so it's harder to save code lines by doing so. Once every possible position has been tested, the variable winner will be either human or computer or 0. If one side has indeed won, a message is printed on the screen and the post-game debrief is carried out by function Postmortem. The program only stores the state of array pattern after the human has moved. What would be the point in storing it after the computer's move? That will be a board position that the computer would never need to respond to. After that, the values of pattern are copied into the first empty slot of array stored position, and the value of num stored is increased to point to the new first empty slot. Note that we can't store the computer's response to the human's move, as that hasn't been worked out yet. The function computer response is so complicated that I've had to split it over 2 screens, I'm afraid. Firstly, the function tests to see if the game is a draw. This can only possibly occur when the last board position is filled and nobody has won. Since the human is the first to move, the last square to be filled must also be a human move. We've already tested to see if the human has won, and if that were the case, function computer response wouldn't have been called in the first place. So all function TestDraw has to do is check to see if every grid position has been filled. OK, let's assume that a draw hasn't happened. What next? Now we score every blank grid position in turn according to both networks, and pick the highest scoring one. To this end, we need a variable max score, initially set to a ridiculously low value, and a variable max position. Max score will end up with the highest score, and max position will identify the blank grid position that gave us that score. The meat and potatoes of the function lies within that innermost loop. Variable a goes through every grid position, with the non-blank ones being ignored. For each value of a, the variable total is initialized to 0. This is where the score for that position will be built up. Then a for loop counts through all the discriminators with a variable b. For convenience, discriminator b for grid position a of the winning net is stored in the temporary variable win_n, and discriminator b for grid position a of the losing net in temporary variable lose_n. The vital line of code is this one. Total is increased by the score given by the winning discriminator, according to the current game position, and decreased by the score given by the losing discriminator. We'll go into the workings of this a little more in a moment. Having worked out the score for that board position, it is compared to the current maximum. If we have a new winner, then max score and max position are updated accordingly. And this is what happens when that loop finishes. At this point, we know which blank square to go for, given by max position, as it has the highest score. Now we can fill in the missing value of stored response that we couldn't before. Note that we store the value of max position in slot numStored -1. This -1 is necessary because the last thing we did in storing the pattern was to increase numStored by 1. Now we have to look back to the previous slot. We store the value computer in the appropriate cell of array GD and update the graphic on the screen. We also change the pair of cells in array pattern to 1 followed by 0 to indicate that the computer has moved there. Or rather, we just change the first one of those values to 1, as the second cell of the pair already contains a 0. Finally, we use checkWinner to see if the computer has won. Here's how that score is found. The function GetAddress takes a single discriminator and reads the 1s and 0s from array pattern that happen to lie at the end of its input connections. These are encoded into a binary number, which is then returned. That number is then used as an index into the values array of the discriminator, and the value in that memory slot is read. I've shown how GetAddress was incorporated into the score from the winning net. You'll recall that the discriminator in question was held in the temporary variable winN. This is passed as the parameter to GetAddress, and the entire function call used as the array index in values. I've included the code for function TestDraw just for completeness. All it tests for is a blank square somewhere on the grid. If there's at least one blank square, then the game is not drawn, at least not yet. In that case, it returns false. If it doesn't find a blank square, it returns true. The function Postmortem is used to update one of the two WISARD nets, WinNet or LoseNet, depending on which player won the game. The actual updating itself is done by function adjust, with the net being passed as the parameter. Function adjust first has to work out which discriminator of that net to update. This will change for each step in the stored game. For the first move the computer made, one particular discriminator in WinNet or LoseNet must be changed. Then change a different discriminator for the computer's second comeback move, and so on. A loop steps through all the stored positions, extracting the positions from stored response. Having obtained the position, we adjust all the winning or losing discriminators for that position. This is what the inner for loop is for. It takes every stored position, turns it into an address for each discriminator, and sets the appropriate slot in that discriminator to 1. That's how WISARD learns. Notice the subtle change in that function from before? That's right. Instead of using function getAddress, which we used for reading the values from the discriminator, you use a variation on that function, getStoredAddress. Function getStoredAddress is essentially exactly the same as function getAddress, except it doesn't read the state of the game grid from array pattern. Instead, it reads it from line stored of array stored position. The parameter stored tells the function which computer response it is, the first, the second, the third, or whatever. Each line of array stored position contains a snapshot of array pattern at that point in the game, and that is the thing used to select the correct values in the discriminators. Phew! It's not a particularly long program, but it is complex and involved. In fact, what I've given you is the barest minimum to get WISARD to play noughts and crosses. The result is a really dull and predictable player. If the human plays the same set of moves, then the computer will always play the same set of moves in response. If several board positions produce the same winning score, then the computer always picks the first such cell. You could put in extra code so that if there are several winning places, or at least bad positions, then the computer will pick one at random. Keep the human player guessing, eh? Of course, one drawback with this current implementation is that it insists the human make the first move. It shouldn't be too difficult to include code so that either player could start. I didn't put it in because I wanted to emphasize the WISARD aspect of the program. One other thing to mention is that this program learns to play excessively slowly. It is possible to streamline things, but I'll let you think about how for yourself. You might want to take a look at the very first project I ever explained on this channel, which, if you recall, was getting the computer to play noughts and crosses by simulating a large number of matchboxes. That's it for this week. Please do click the like button for this video if you think I made a half-decent job of it. and share the video with anyone you think might be interested by it. And of course, I would appreciate a comment down below.